In this video, I am going to explain ES or spectroscopy. This is the MSc syllabus from Karnataka State Open University, 4th semester, Unit 6. In this unit, we have to learn the concept of ES or spectroscopy. ES or means electron spin resonance. In this, we have to discuss the characteristics of Z value, types of ES or spectroscopy, presentations of the spectrum, Z value of an electron and a complex, factors affecting Z value, CFS and LS coupling, zero field splitting, Cronner's degeneracy, hyperpoint splitting, ESR of transition metal complex exhibit D1, D2, D4, D5 systems, applications of ESR spectroscopy of biochemical molecules, means iron proteins, copper proteins, manganese proteins and cobalamin. Finally, summarize the unit of ES or spectroscopy. The term ESR means electron spin resonance. It is a spectroscopic method for studies of paramagnetic species. Paramagnetic means the species which is having unpaired electrons in d orbital, or the complex it is having a unpaired electrons in that d subshells or d orbital. This ESR spectroscopy is related to that nuclear magnetic resonance technique. Both methods make use of magnetic properties. In the first case, electrons. In the second case, nuclei. The microwave technique in this frequency range of this ESR is 109 Hz and higher, that is normally employed in ESR instruments, had been developed for radar detection units during the Second World War. The systematic studies of transition metal salts began at the end of 1940s. In this, the free radicals or molecules with an unpaired electrons have been tracked and identified, and their reactions followed by both in the liquid and the solid state in many instances. Such studies are still ongoing. Nowadays, more as one tool in conjugation with other methods to obtain chemical informations. What is the basic theory of this ESR spectroscopy? When a paramagnetic molecule observes a quantum of electromagnetic radiation in the microwave region, electrons is excited from one energy state to another spin energy state, which is higher energy state. This is lower energy, this is higher energy. Generally, electron is in that lower energy state. Once it is gaining of energy, what it becomes what? Higher energy state. The electron spin value is plus or minus half. That is indicates that equal energies of lower energy and higher energy. Here, the transition will occur between the two states, lower energy state and higher energy states. The energy of the quantum of radiation is equal to difference in energy between the two spin states of the electron. Mathematically, that is represented by the equation is delta E is equal to h mu. That is also written as G beta h naught, where h is the Planck's constant, mu is the frequency of radiation, B is the Bohr magneton, where H naught is the external magnetic field strength, and G is the spectroscopic splitting factor. Generally asking in the 2 mark questions, what are the characteristics of G or splitting factor? This G is not a constant. It is a tensor quantity. It depends on 3 parameters, namely magnitude, directions, and arbitrary number of indices. For free electrons, the spectroscopic splitting factor is 2.00234. In metal ion, the G values often greatly differ from the free electron value. The magnitude of G depends upon the orientation of the molecules containing the unpaired electron with respect to the magnetic field. In solutions or in gaseous phase, the G is averaged overall orientations because of the free motions of the molecules. If the paramagnetic radical or ion is located in a perfectly cubic crystal site, the G value is independent of orientation of the crystals and is said to be isotropic. In the crystals of lower symmetry, G value depends on the orientation of the crystals with respect to the magnetic field and is said to be isotropic. The Z direction coincides with the highest fold rotation axis. It is determined by X-ray techniques. When the Z-axis is parallel with the external magnetic field, the G value is called G parallel. It is known as ZZ. The G values along the X and Y axis are called Gx and Gy. These are referred to as G perpendicular. The reason is that external magnetic field is perpendicular to the Z-axis. For that tetragonal site of this molecule, the Gx is always equal to Gy. If theta is the angle between the magnetic field and the Z-axis, the experimental G value is given by the following equation for a system with axial symmetry. G square is equal to G parallel square cos square theta plus Z perpendicular square sin square theta. There will be inequality in G values even if there are small distortions. These cannot be detected by X-rays. However, ESR cannot detect these small distortions from the inequalities in G values. ESR can detect these small distortions from the inequalities in G values. This is the characteristics of this splitting factor. Next, we will move on to that. What are the types of ESR instruments? There are two types of ESR spectrophotometers. X-band spectrometer, Q-band spectrometer. In that X-band spectrometer, a frequency around 9,400 megacycles per second and a magnetic field strength around 3,000 Gauss are employed. The magnetic field strength can be varied in the range 1 to 10,000 Gauss. Q-band spectrometer, a frequency around 35,000 megacycles per second, a magnetic field strength around 12,500 Gauss are used. What is the spectrum? Yes, spectrum representation. The ESR spectrum is represented in two modes. One is that normal mode and another one derivative mode. In this normal mode, the absorption intensity is plotted against magnetic field and curve. Absorption intensity is plotted against the magnetic field. That is what normal mode. In this mode, the absorption intensity is plotted against the magnetic field. A curve has shown. The disadvantages is that the absorption band are broad, like that. We are getting what? Broad. In that derivatives mode, the first derivative of the absorption intensity di by dh is plotted against the magnetic field. The curve is obtained. The advantage of this curve is that this type plot is more accurate. When the absorption intensity is maximum. The derivatives curve crosses the x-axis. The number of peaks in the absorption curve corresponds to the number of maxima and minima in the derivative curve. This is what derivatives curve of this ESR spectrum. Next, how to find that G value for an electron and a complex? It is an inherent property of a system containing an unpaired spin, similar to the chemical shift observed in an NMR spectrum. The G value for a single unpaired electron has been calculated and experimentally determined. The G value for a S is equal to half system is usually near G, but it is not exactly at G. This is due to spin-orbit coupling, which determines both the value of G and its anisotropy. The Z value can be often calculated with the formula. Here Z is equal to 1 plus G into G plus 1. Yes. S plus 1 minus L plus 1 by 2 J plus 1. The free electron S is equal to half, L is equal to 0, J is equal to S is equal to half. That Z is equal to 2 into J into L plus S. The factors affecting Z value in a complex: the nature of the metal, geometry of the complex, relative magnitude of spin-orbit coupling, the crystal field. These are all what factors affecting the G value. Here, nature of the metal we consider here n number of metals are there. Here 5D series and 5D series elements are there. 4D, 5D, 6D different. The geometry of the complex means ligands and their arrangement. Crystal field splitting in term actively and the electronic level, hence the ESR transition. These are all representations of this ESR. Next, effect of spin-spin coupling. When unpaired electron is placed in a chemical environment or in a transition metal complex, the Z value does not agree with the expected value. The crystal field effect on that Z value, crystal field is not affecting the 4f and 5f electrons. So, ESR spectra of the lanthanides. The actinides are quite simple. If iron contains more than one unpaired electron, CFS may operate. Zero field splitting. ZFS means what? Zero field splitting. These three can be distinguished: spin orbit coupling is very much greater than the crystal field. The effect of crystal field is strong enough to break the coupling between L and S. Effect of crystal field is very large, so that the LS coupling is broken down completely. These are all different cases regarding to the Z value. This Z value is also affect some factors: operating frequency of the instrument, concentrations of unpaired electrons, ground term of the metal, direction and temperature measurement, inherent magnetic field in the crystals, John Taylor discussion. These are all what other factors affecting the Z values. Sustaining effect. Sustaining effect means the spin angular momentum S of electron tries to couple with the L. This partially retains the orbital degeneration. The crystal field rises to quench the L values and S tries to restore it. This phenomena is called what? Sustaining effect. Depending upon the which effect dominates the L value, deviates from the original value. The L and J is not a good quantum number to denote the energy of electrons, hence the value also. What are the combining effect of this CFS and LS coupling? The LS coupling is greater than CFS. The CFS is greater than LS. And CFS is very, very less than LS. LS coupling is greater than CFS. When L is not affected much CFS, then J is useful in determining the G value. The CFS is greater than LS coupling. Here, break LS coupling, then J is not useful in determining Z value. In case of CFS is very, very greater than LS, consider that strong field LS coupling is completely broken and L is equal to 0. Means there is no covalent bond. This is applicable to 3D strong field, 4D and 5D series. In many cases, MOT gives fair details than CF. These are all some examples regarding to that. Just to see here, this is the ESR spectra of these copper 2 ions in various field. This is triennial, this is octahedral field, this is tetragonal field. We consider other systems like that D1 system. D1 means atomic number of titanium is 23. Generally, these type of systems arises titanium and vanadium oxide. Here also the energy gap is very less, vibration makes these levels so T is very low, leading to prone broad lines. Next we'll see that D2 systems, D3 system, D4 system. That is what? Weak field. What is G value and structure? The G value can obtain very important information about the structure of complex. For a complex in solution, G is average to overall orientation because of the free motions of the molecules. In that cubic field, metal ligand bond length are the same along the three Cartesian axes, and hence Z remains the same. Next we consider the tetragonal field. If the crystal field is tetragonal, the metal ligand distance along the x and y axis are the same but different from the metal ligand distance along the z axis. In that rhombic, if the symmetry is rhombic, three different G values are obtained, that is Gx not equal to Gy not equal to Gz. In Bharat's acceptability measurement, a powdered sample is used and G works out as an average. If a well-formed single crystal is used, the ASR measurements can provide the G values based on the orientation of the crystals. Next, zero field splitting. When the spin levels are split even in the absence of magnetic field, it is called zero field splitting. Spin levels are split even in the absence of magnetic field are called zero field splitting. When the metal ion is placed in a crystal field, the degeneracy of the d orbitals will be removed by electrostatic interactions. The d orbital degeneracy means here the d orbitals it undergo dividing into two, one is that lower energy and another one is higher energy. In that lower energy dxy, dyz and dzx, in that higher energy level dx square minus y square and dz square. That is the crystal field removes the orbital degeneracy. However, the spin degeneracy is not removed until a magnetic field is applied. The splitting of electronic levels, even in the absence of external magnetic field, is possible due to association of distortions and LS coupling. This is called zero field splitting. The splitting may be happens when there is strong dipolar interactions of the first level is raised in energy, this dipolar shape reduces the gap between S is equal to 1 and S is equal to 0. Now two transitions do not have the same energy, resulting in two lines. Next, Kramer's degeneracy. That is one of the very important. Systems with even number of unpaired electrons will contain a state with S is equal to 0. But in the case of odd electrons, no state with S is equal to 0 appears, since Ms is equal to half. In such case, even after CFS, the spin state with opposite Ms values remains degenerate which is Kramer's degeneration. The levels are called Kramer's doubles and in any system with odd numbers of unpaired electrons, the zero field splitting leaves the ground state at least two-fold degenerate. This is zero field splitting on magnets. This the spin degeneracy can be removed by magnetic field in one unpaired electrons is present. Crystal field if more than one compound electron is present. This is odd number Kramer's degeneracy applies and each level this is what even number crystal field removes. The spin degeneracy complex non-degenerates. This is one of the very important molecules. Consider a molecule, two unpaired electrons, then S is equal to plus of and plus of is equal to 1. Therefore, Ms is equal to minus of 0 and plus 1. Next we consider the first transition what happened here, minus 1, 0, 1. Here Ms is in that 0, here Ms is equal to plus 1. Ms is equal to 0. The Kramer's degeneracy is not operative. That is, each level will be doubly degenerate. If zero field splitting is present, it removes the degeneracy in Ms as shown. These are other representations of this Mn plus. What are the consequences of this zero field splitting? In some cases, zero field splitting magnitude is very high than the splitting by external field. Then transition requires very high energy. Sometimes only more transition occurs. For example, vanadium 3 plus, vanadium 4 plus. The CO2 plus in cubic field has a ground term of 4F. Since it is a D8 system, it have 3 by 2, 1 by 2 levels. The splits the levels by 200 per centimeter. Since the energy gap is higher, only the transition minus half to plus half. It's seen. How to break down of selection rules? In some cases, the magnitude of JFS is very high, hence it exceeds the normal energy range of ESR spectrum. In such systems, normal transition occurs with delta Ms is equal to plus or minus 1. But this energy exceeds the microwave region. Then the transition from minus 1 to plus 1 levels with delta Ms is equal to plus or minus 2 occurs, which is a forbidden one. Next we look at that mixing of states. The magnitude of the zero field splitting can be taken as orienting from CFS, but orbitally singlet state S is not split by the single field. Even then, Mn2 plus shows smaller amount of ZFS. This is attributed to mixing of GS and ES because of LS coupling. Next, what is the magnitude of zero field splitting and signal? The effect of moderate zero field splitting is shown in that figure. When zero field splitting is very large, the allowed transition Ms is equal to plus or minus 1 becomes too large that be observed in the microwave region, that is Ms is equal to 0 to plus 1. These are all the moderate zero field. This is large keto field splitting. For the effective spin here, consider a metal in a cubic crystal field. In zero field splitting, where operative towards transitions would be expected. For example, nickel 2 plus, it is in D8 configuration, which has 3 Ag2Z ground state in an octahedral field, and in some cases gives rise to 2 transition in the EPR spectrum. What is the mixing of states and zero field splitting? The other thing is hyperfine splitting. When the unpaired electrons comes in the vicinity of a nucleus with a spin I, and interactions with it takes place, which causes the absorption signals to be what is the reason for that? Here, the nuclear spin resonance spin coupling arises mainly from the Fermi contact term. The 2 energy levels of a free electron in a magnetic field are given. This is selection rule. Positive M means Ms is equal to minus of, Ml is equal to plus or minus of, will have lower energy. A negative means Ms is equal to minus of and Ml is equal to plus of. Will we have lower energy. Sign of A cannot be determined from a simple spectrum. Magnitude of splitting is expressed in terms of coupling constant. The magnitude of A depends upon the following. These are all what? Characteristics of A. What is hyperfine splitting in various structures? This is hyperfine splitting in various structures. They are given here. The spin lattice relaxation, causing line broadening is that there is the paramagnetic ion interactions with the thermal vibrations of the fluid. Next we consider spin relaxation. In that spin relaxation, this result from the small magnetic field that exists on neighboring paramagnetic ions. As a result of these fields, the total field at the ions is slightly altered and the energy levels are shifted. This is the calculations of Z parallel and Z perpendicular for these two states. Ground state is equal to dz square. This means that copper 2 unpaired electrons is in the dz orbit, that is Z in distortion and compressed. Where lambda is the spin orbit coupling constant of the free ion. Here lambda is the negative because the system is more than half filled. Since Z value will be greater than 2. Therefore, for a tetragonally compressed copper 2 complex, Z perpendicular to the Z parallel, in that ground state, D x square minus y square. This means that unpaired electron is in that D x square minus y square orbital. This orbital has the highest energy. This becomes the ground state in terms of the pole. These are all the mathematical expressions and observations can be summarized in that dz square, that is compressed Z in Z perpendicular to Z parallel. In dx square minus y square elongated, here Z out, here Z parallel greater than Z perpendicular. In that ESR spectrum, the Zahn-Teller distortion is the major or important topic. Zahn-Teller theorem states any nonlinear electronically degenerate system is unstable. Hence, it will undergo distortions to reduce the symmetry, remove the degeneracy, and hence increase its stability. But this theorem does not predict the type of distortions. Because of Zahn-Teller distortions, the electronic levels are split and hence the number of ESR lines may increase or decrease. This is ESR of transition metal complex. When ligand is approaches to the central metal atom to formation of a complex molecule. Due to the presence of this variable oxidation state and exhibit or which contains unpaired electrons in that d orbitals, the transition metals are easily complex with ligands molecule. All the complex have that Cramer's depth doublets are close in energy. This leads to a short relaxation time, etc. We consider that examples of this is titanium sulfate molecule, that is in undiluted. In the above compound, titanium is 3 plus, Z perpendicular is 1.24 and Z parallel. Z parallel is 1.24, Z perpendicular 1.14. The ASR signal may be obtained only at low temperature. In the ground state of 2T2Z term is J is equal to 1.5 and where G is equal to 0. However, the above experimental G values have been obtained due to tetragonal or trigonal ligand fate component of magnitude compatible to lambda for the ion. This is the following another example. This is given tetrahedral molecule. In tetrahedral ligand field, the ground state is e power 2. It has no first order spin orbit coupling. In this geometry, the ground state mixes with the nearby T2 excited state by second order spin orbit coupling. This leads to a short spin relaxation time for the electron and broad absorption lines. When the ligand field is distorted, this is the example of this molecule. In that D2 system, here 3T1Z, the ground state is 3T1Z. Expansive spin orbit coupling is present in this state. Therefore, ASR is usually not absorbed. The configurations approximate to cubic symmetry in the octahedral complex. In D2 system tetrahedral, it is a ground state and no spin orbit coupling. The relaxation time will be longer and so ASR signal is absorbed ready. The D3 systems in ground state, term is 4 to AZ, S is equal to 1/2. S is equal to 1/2 since more than one unpaired electron is present. Zero field splitting will take place. The number of unpaired electron is odd and hence Cramer's degeneracy will be applicable. That is, each level will remain or doubly degenerate. As a result, Cramer's doublet will be the lowest in energy when the zero field splitting is small as shown in the figure of this D3 system. This is D4 system. That is almost similar to that. This D5 system. Here spin free complex is S is equal to 1/2 and for spin pair complex S is equal to +half. G is isotropic. The very small zero field splitting is neglected. The absence of zero field splitting follows from the fact that there is no extent term other than ground 6A1Z term. is the example for that. In spin paired, that is D5, that is potassium hexacyanoferrate, that is diluted with that potassium cobalt cyanide. Z perpendicular and Z parallel values they are given. The signal may be obtained at very low temperature. These results indicates the presence of liquid ligand field component to low symmetry of magnitude less than the spin orbit coupling, together with a small amount of T2Z electrons delocalization. They are represented here. Now we are going to discuss with some important applications of biological molecules. One is that iron proteins. Iron is the single most abundant metal in biological systems, occurring mostly in respiratory proteins. Hemoglobin and myoglobin are two important bound of iron containing proteins. The strategic presence of iron in the heme facilitates transportation and storage of oxygen by the two proteins. This is how to detect that proteins molecule. This is first derivative X-band EPR spectrum for hemoglobin, showing high spin features of iron 3 at G is equal to 6, low spin feature is equal to 2.885 midfield. Next we consider this copper proteins molecule. Naturally abundant copper proteins include ceruloplasmin, hemocyanin and cu-bis-zn superoxide dismutase. The copper-2 is a D9 species, contain an odd number of electrons to give a spin. S is equal to half, and therefore EPR transitions are absorbed. Then the magnetic moment M1 is equal to 3 by 2. Copper gives a spectrum comprising a quadret of lines. This is magnetic field in Gauss. The first derivative EPR spectra for copper-2 showing different G values and A values for different structural environments. This is manganese proteins. The manganese occurs in much smaller amounts than iron and copper in nature. As a contributor to electron transfer in the oxygen evolving photosystems, manganese is widespread in plants. Its presence is easily determined by EPR based on manganese 2. D5 S is equal to 5 by 2. On interactions with nucleus, a characteristic set of 6 isotopic lines is obtained, centered close to free spin. Just to see that figure 6, here in that manganese 2 lines obtained from tobacco leaves at 77 K. The mitochondrial superoxide dismutase enzyme contains manganese, though this is far less abundant than the copper zinc systems. This EPR spectrum for manganese molecule shows featured ascribed to high speed. Manganese 3 and manganese 4 and probable higher oxidation states are reported to be present in catalysis. In cobalamin is also known as vitamin B12. Is an organic molecule in which cobalt is 4 coordinated at the center of heroin group. A smaller heme type structures with 4 nitrogen donor positions. The 5th position is N linked to dimethyl benzene 2, which is attached to ribose 3-phosphate oxygen linked to aminopropanol. The 6th position is occupied by the 5-deoxyadenosine, but can be replaced by other substitutes as in the different derivatives of cobalamin. The CO nuclease has D5 configuration with spin S is equal to half, and a paramagnetic or magnetic moment is 7/2. The EPR spectrum comprises 8 lines that is observed in that figure. In spite of apparent similarities of the heme and heroin structures, iron and cobalt are not biologically interchangeable. This must be due to their redox potentials being different in different discriminators. This is what diagram of this vitamin B12. This is peak assigned or spins values are mentioned here. The ESR spectrum of phosphates, the quantum chemically calculated to expose of minimum energy is distorted trigonal bipyramidal with 2 axial and 2 equatorial hydrogen atoms. The unpaired electron is placed at the position of the missing equatorial ligand. From quantum chemical calculations revealing the significant odd electron density to reside on the axial positions, it was shown that metastable structure B as shown in the figure. This is considerable evidence that the basic structures of free radicals derived from tetravalent phosphorus is that of a distorted trigonal bipyramidal in which 2 ligand sites, apical and equatorial, are distinguished. The ESR isoform interaction shows a striking disparity between the unpaired spin densities at the 2 positions, and theoretical arguments favor the apical positions as having the higher spin density. Now I am going to summarize this unit. The ESR spectroscopy, it is also referred to as electron paramagnetic resonance, simply that is EPR spectroscopy. is a versatile, non-destructive analytical techniques based on the absorption of microwave radiation in the presence of an applied field by paramagnetic species. When any species that contains unpaired electron is subjected to static magnetic field, the interactions between the magnetic moments of the electron and the applied magnetic plates, the spin energy levels means Zeeman splitting. The transition between the spin levels are induced by applying suitable microwave radiation perpendicular to the magnetic field. Further interactions will depend on the presence of other factors such as the nuclear spin present in both the origin and other neighbors. The resulting absorption of the microwave radiation is modulated to record the spin derivative of the absorption. Conventionally, EPR spectra are recorded as the first derivative rather than absorptions to improve the resolutions. In fact, the second derivative's operation is also possible when needed to get better resolutions of complex splitting patterns. These are all important self-understanding questions. Please go through these questions. These are all very important in the point of examinations. Explain the basic theory of EPS or spectroscopy, characteristics of Z, write a note on Z values for an electron and a complex, factors affecting Z value in a complex, combined effect of CFS and LS coupling, Z value and structure of complex molecule, zero field splitting and Kramer's degeneracy. These are all important things. Question: iron proteins, yes, or spectroscopy of that iron proteins, copper proteins, manganese proteins, cobalamin or vitamin B12, finally phosphate radical. Thank you.